Discovery 频道，开拓您的世界。
The earthquake. Sudden, unexpected, terrifying. No other force of nature can produce destruction like this. No other force kills so many. When it strikes, there's nowhere to go. We can try to prepare ourselves, but the real thing is deadly. We can only hope we survive the most destructive force on our raging planet. Earthquakes are the most sudden, unexpected, and destructive force of nature. They strike without warning. The ground starts to shake, and there is simply no way of knowing when it will stop. It might be a small tremor or a huge once-in-a-lifetime quake. Either way, you cannot escape it. You can only hope you survive.
And it just kept coming, and it kept coming, and it kept coming again. And it was like riding a roller coaster. It was really a rocking and rolling. I just, in my wildest imagination, had no comprehension that Mother Nature could be that destructive in just, you know.
If there is one thing in life we take for granted, it is the earth beneath our feet.
I looked out and the crack just suddenly opened up, and it just was so quick. It was just like a rifle shot. It just, boom, it was open.
When the earth moves, when the world around us literally collapses, the terror is absolute. No other force of nature can cause so much damage in so little time. In this century alone, earthquakes have killed more than 2 million people. Yet in total, the earth shook violently for less than 1 hour. Earthquakes are very common. Around the world, there are up to 1 million a year, but most of them are too weak to be felt. In an average year, there may be a few hundred quakes which cause minor damage, and between 1 and 20 major earthquakes. This is central Italy, October 1997. An earthquake struck a wide region in the middle of the night. It caused damage to many buildings and 6 deaths. Ten hours later, the first of several aftershocks hit. It was much stronger than the first tremor. Hundreds of houses collapsed. In one village, the whole population was made homeless.
Sì, non c'è stato mai. Qualche fossetta così, ma poca roba. Forse così non c'è stato mai.
Quella della notte uno non si rendeva conto, perché dormivi e sentivi che ti urlava la casa e non ti rendevi conto. Quello del giorno e vedevi quelle case che sembrava che ti venissero addosso.
The aftershock brought tragedy to the 700-year-old Basilica of St. Francis in Assisi. After the original quake, a group of monks and others were examining the beautiful frescoes on the walls and ceiling for signs of damage. While they were working, the aftershock struck. Part of the ceiling collapsed on them, killing 4 people. Without people, earthquakes would pose no threat. In an uninhabited region, even a major tremor may leave no sign that it ever happened. But this is a crowded planet. Many regions prone to earthquakes are also full of people. Urban areas are becoming larger and more complex. Cities are growing all the time. A large earthquake in a crowded urban area could kill more people in a few seconds than any other form of natural disaster. Today, an estimated 600 million people live in areas where damaging earthquakes occur. They live with the risk that their homes and lives may be destroyed at any moment. It's a risk that becomes just part of life. This is the signature of an earthquake, recorded by an ultra-sensitive seismograph buried deep in the ground. Any quake anywhere causes the whole Earth to vibrate. This one could be happening hundreds or thousands of miles away, even on the other side of the planet. At the National Earthquake Information Center in Colorado, every significant tremor on Earth is recorded. Data is beamed in from seismographs all over the world. The center analyzes the information and alerts authorities about the magnitude and scale of each quake. When an earthquake occurs, the first waves to arrive are the fast pressure, or P waves. Alarms go off all over the building to alert the scientists. The instruments register the shock waves from different parts of the world.
Here's a P arrival here. P arrival here, P here. See all this is New Hampshire. There's a P there. This earthquake, I think, is not in the United States, but it's a pretty big quake. Probably, maybe south. This is just coming in. We don't even know where it is yet. This is an earthquake. This is the type of thing that just happened. We talk about prediction. We didn't predict this. We cannot predict. We cannot forecast. The earthquake is occurring.
The computers then pinpoint the exact location and magnitude of the quake within minutes.
We got so far as Panama or Colombia border.
This information is then sent automatically to key personnel via their pagers.
Just a moment, I'll get it for you. 7.4 degrees north. Origin time is 17 hours, 25 minutes, and 00 seconds.
The first seismic detector was invented almost 2,000 years ago by a Chinese mathematician. He built a device with metal balls and dragons' mouths. A pendulum in the instrument moved when it registered a quake, and the balls fell out into the waiting frogs' mouths below. The Chinese were unique. Other cultures relied on religion and mythology to explain earthquakes. The early Japanese spoke of a giant catfish that fought with a god. The god won and stood in triumph on the great fish's head. From time to time, the catfish thrashed around, and the drumming of its huge tail shook the ground. Modern science gives us a more rational explanation, but it too shows us just how small we really are. Earthquakes happen because on a vast, slow scale, the entire surface of the planet is in motion. The Earth's crust is divided into broad pieces called tectonic plates, floating above the liquid mantle hundreds of miles below. These tectonic plates are constantly moving, driven by convection currents in the mantle. The movement is incredibly slow, about half an inch per year, or just about the speed that fingernails grow. In some parts of the world, the plates collide. One plate slides under or past the other. The immense forces push up the crust, forming mountains and volcanoes. 95% of all earthquakes happen along the boundaries between tectonic plates. So it's not surprising that one of the largest earthquakes in recent years occurred where the Pacific Plate is moving past the continental American plate. It was Alaska in March 1964. The earthquake struck along a fault line 500 miles long. Shaking was felt for almost 7 minutes, an incredibly long time for an earthquake. The town of Anchorage was hardest hit. The force of the quake was so great that the ground itself was torn up for miles. In places, the land sank 50 feet. The amount of energy released was the equivalent of 12,000 Hiroshima-sized atomic bombs. Fortunately, the area was sparsely populated, but still, 115 people were killed. Southern China also lies at the edge of the same Pacific Plate. It was hit by a much weaker earthquake in 1976, but this quake struck near the surface and hit a densely populated region with many poorly constructed buildings. More than 250,000 people died. Another 800,000 were injured, and several million were made homeless. Moderate tremors at shallow depths usually cause much more damage than larger, deeper quakes, because the shaking is transmitted to the surface quickly and without much loss of energy. Wherever they happen, the causes of earthquakes are the same. When two tectonic plates move against each other, there is enormous friction along the line between them, known as a fault. If the rocks on either side of the fault become locked together, huge amounts of energy build up as they strain to get past each other. Time passes, a few years, or maybe hundreds, but eventually the plate movement breaks the grip between the two sides of the fault. The plates move, suddenly and rapidly. On the surface, there is a violent rippling of the ground. An earthquake has occurred. Perhaps the most famous example of this type of fault is the San Andreas Fault in California. Everywhere along it, there is evidence that the earth is moving. This is Hollister, California. Here in the leafy suburbs, a major force of nature is revealed by a bend in the sidewalk. It may not look much, but this curved wall was straight only 5 years ago. The fault passes right under the wall on the sidewalk. One side is moved relative to the other. Placing a building across the fault is asking for trouble, but that's what happened with this winemaking factory. Here in the farmland outside Hollister, the line of the San Andreas Fault is less obvious, but still visible along the line of trees at the bottom of this valley. This is rich grape-growing country with a local vineyard. Unfortunately, the people who built the winery had no idea that the flat land at the bottom of the valley hit a major tectonic fault. They built the winery right across the fault. The building completely straddles it. So, in addition to making fine wine, the owner has to deal with the fact that the building is slowly being torn apart, one half traveling in the opposite direction to the other. Structural repairs help temporarily, but the future is bleak. If there is a major earthquake along the San Andreas Fault, the building stands little chance. October 1989. another part of the San Andreas Fault, this time under the Bay Area of San Francisco. The Loma Prieta earthquake was the biggest tremor to hit the region since the Great Earthquake of 1906. San Francisco lives in constant fear of earthquakes. This time the city was lucky. 63 people died. But it could have been far worse. Several miles of roadways and hundreds of buildings collapsed or were damaged beyond repair. This quake was less severe than it might have been. Some scientists had forecast that the stresses in the fault would build up to one giant earthquake. Instead, the fault may be releasing its stored energy in a series of smaller tremors. One thing is certain, though. The San Andreas is a highly active fault, and violent tremors could happen at any time. Along the San Andreas Fault, the two plates are moving laterally. But the hills around Los Angeles hide another danger: vertical faults, where one plate is pushing up against another. Seismologist Lucy Jones is someone who understands the potential for disaster in Los Angeles.
Los Angeles is a major world city sitting at the conjunction of two major fault systems. We have the strike-slip faults of the San Andreas Fault coming up from the southeast into Los Angeles, and we have the thrust faulting systems of the transverse ranges that create these mountains that we're standing on. And in the transverse ranges, one set of rocks are being pushed up and over the set below it.
In January 1994, one of these faults did slip and caused the Northridge earthquake.
Hello, is anybody there?
No one even knew this fault existed.
This is all the first floor underneath it. This is the second floor right here. See underneath us? Yeah. Is anybody in there? Okay. Keep on going through.
There were only 72 deaths, but the Northridge quake injured 7,000 people and left another 20,000 homeless. It was also the most expensive quake in U.S. history, with over $30 billion in damages. Around the world, there are many cities where large earthquakes have occurred and where scientists know they will happen again. But how could a major population center survive a huge tremor? Most modern skyscrapers in earthquake hazard regions, like these in Tokyo, are built to withstand the most severe earthquakes. The engineers and architects are confident that the thousands of people who work and live in buildings like these will be safe. But will they? Can we really be so sure? It's the complexity of urban life that makes us so vulnerable. Tokyo has 14 million inhabitants. Other cities have more. And in any city, there are thousands of buildings which are not protected against earthquakes. So, if a large earthquake happens near one of our major centers of population, what are the likely effects? In the 1985 Mexico City quake, over 400 buildings that were designed to withstand earthquakes collapsed. They were mostly between 6 and 16 stories high. The tremors caused vibration in the structures and the buildings just shook themselves to pieces. Inside every single building, the contents are tossed around as if they were in a doll's house. Even in the strongest office block, hundreds of people will be crushed or killed by falling objects. But outside is no safer. Masonry, roof tiles, signs, and most dangerous of all, glass, all come crashing down. Every modern office building contains hundreds of square yards of glass windows. Even if the buildings themselves withstand the shaking, many panes of glass will break and rain down in a deadly shower on anyone caught in the streets below. One of the greatest earthquake dangers is fire. Overturned cooking stoves in homes, broken gas mains, severed power cables. Water mains will also shatter, so the emergency services might not be able to get water to fight the fires, and floods could become yet another problem. In every major earthquake of recent times, fires have been one of the worst causes of destruction and death. In the 1995 Kobe earthquake in Japan, which killed more than 5,500 people, fires raged across the city for several days. And in a crowded urban environment, there is a far greater danger once fires get out of control: the firestorm. As the flames fan upwards, they suck in air. The rushing air creates winds of more than 100 miles an hour, which fan the flames still further. It's a deadly, vicious circle. In the Great Tokyo earthquake of 1923, a firestorm killed more people than the earthquake itself. 40,000 survivors of the original quake had been sheltering in a park about the size of a football field. Then a firestorm swept through that part of the city. Of the 40,000, only 30 people survived. There are other side effects of earthquakes. The worst is the tsunami or tidal wave. They're created when an earthquake shakes the ocean floor and moves a vast quantity of water. The Alaska earthquake of 1964 created a tidal wave which killed more people than the earthquake itself. The scene after any earthquake in a major city is complete devastation and chaos. In Kobe, whole office buildings fell into the streets, completely blocking the roads and making it impossible for emergency relief to reach many districts for days. When buildings collapse, many people are killed and trapped. In Mexico City, one of the greatest tragedies was that several hospitals collapsed, killing patients and medical staff alike, and rendering the hospitals unusable just when they were needed most. For anyone driving at the moment an earthquake strikes, a modern city is not a safe place to be. Apart from the dangers of falling objects, elevated roadways are particularly dangerous. This happened in the 1989 Loma Prieta quake, and also in Kobe in 1995. Several huge sections of road toppled over, throwing many vehicles over the edge and crushing many more. The collapse of these roads alarmed engineers around the world because the elevated stretches were designed to withstand bigger quakes than the ones which destroyed them. Somehow, the roads were still vulnerable in ways they didn't understand. Earthquake damage varies so much, it sometimes seems to make no sense. In Kobe, some buildings were completely destroyed, while those on either side remained untouched. In some cases, this can be explained by the quality of design. Deep foundations and strong reinforced construction can help a building withstand the shaking. Unfortunately, many developing countries lie in earthquake zones, and the quality of house construction is poor. A fairly minor earthquake in western Peru in 1996 destroyed or damaged thousands of homes because they were simply built of unreinforced brick and weak cement. Several dozen people died here. In homes built in America or Europe, they would probably have survived. But even in earthquake-aware California, there have been surprising collapses. In the 1989 Loma Prieta quake, many large apartment buildings in the Marina district of San Francisco were destroyed or badly damaged. Maureen Brunna lived in one of them.
The force of the initial shock just catapulted me down to the floor. I reached up, pulled the door open, and I pulled myself up into the door frame. And then in the next few seconds, the door frame started to come off in my hands. And I realized at that point that I'd better get out of the building because the building was possibly going to come down. And so I just started crawling on my hands and knees, and I went down a flight of stairs, and I crawled out of the building.
The problem for the Marina district was that the homes were built on wet coastal land which had been filled in. When the area was shaken by the quake, a phenomenon called liquefaction occurred. When water-soaked land like this is shaken, the water rises up towards the surface, and the ground starts to behave like a liquid. Houses will slowly sink, no matter how solid their foundations are. Some earthquakes hit buildings of a certain height the hardest. This happens when the frequency of the earthquake waves corresponds with the natural vibration frequency of the structure. These buildings will then shake much more than others. It's hard to know exactly why some buildings are destroyed while others survive. We do know that building on solid rock is better than building on sand or clay. But in some cases, there is just no good explanation. For the survivors of an earthquake, the first reaction is usually shock.
Go home! We've had serious problems, obviously. Go home and secure your residence. Shut off the gas, shut off electricity, store water, prepare for
aftershocks, prepare for 3 days of no services. You got 90 minutes of light left. You better make use of your time. Standing here ain't doing nothing.
I was in shock. I was really in shock. I sat on the curb, and it's strange the things that go through your mind at a time like that. I was thinking, gosh, I don't have my makeup. You know, that was like the first thing. What am I going to do without my makeup? I don't have any identification. Who am I?
The frustration is understandable. Sometimes the destruction of people's familiar environment is so traumatic, they just can't deal with the situation. This is Armenia, December 7th, 1988. Here, the ground shook for just 40 seconds. Whole towns and villages were flattened. 25,000 people died. 500,000 were made homeless. The devastation was so great that the survivors just could not comprehend what had happened.
Жена, дети, мать, отец. Все нет их.
The Armenian earthquake was one of the worst to hit the region in recent years, although tremors there are common. An active tectonic plate boundary runs across southern Europe, from Portugal through Italy, Greece, Turkey, Armenia, and Iran. All these countries are vulnerable to large earthquakes. After a major earthquake, the most immediate priority is to find any survivors buried and trapped in the rubble. This is always a race against time. Rescuers use whatever technology they can to break through to where people may be trapped. Dogs are especially useful in locating buried survivors. Finding anyone alive is important psychologically. It's a message of hope at a time of deep despair. This man survived for 3 days in the wreckage of a supermarket. Victims are often very badly injured. Dehydration is common. Very few people survive being trapped for more than a few days.
Мать, никак не могу вытащить. Может, она была жива, но за эти 7 дней она уже может... Все.
Нет крана, да, нечем тащить.
The next sad but inevitable task is digging out the dead. For weeks after the Armenian quake, coffins were all the authorities could provide for the surviving relatives, who had to locate and remove the bodies themselves. Their grim task was made even more difficult because the earthquake happened in early December, when the weather was freezing. Food supplies were scarce, and it took most of the survivors' energies to stay alive, let alone search for the bodies of their loved ones. Occasionally, there are extraordinary stories of survival. After the collapse of a hospital in Mexico City during the 1985 quake, several newborn babies were found still alive after a week's burial. Babies retain fluids well, which certainly helped, as did a reflex in the very young which puts their bodies in a state of suspended animation when traumatized, the so-called diving reflex. Whatever the reason, finding these children alive after so long brought a ray of hope to the weary rescuers. After a big tremor, many survivors spend days or weeks out in the open, despite sometimes appalling conditions. They refuse to return to their homes, even if they're undamaged. They fear aftershocks. Most earthquakes consist of one large tremor, followed by many aftershocks, which can occur hours, days, or even weeks later, as the fault plane settles down to its new position. In 1992, an earthquake in California damaged the telescope in this observatory.
Holy cow! Holy cow! Oh my God!
But this video isn't the main tremor. It's an aftershock. It was taped on the day after the quake by a member of the staff. He'd returned with a camera to survey the damage. As he taped, the aftershock struck.
I'm okay! Oh my God. All right. I'm on my way out. Stand by. I'm on my way out. Top floor. What happened to the top floor? Destroyed. What do you go? Come on. It may fall off. Go. Get it, man. Come. I got it on tape. Oh. I got it on tape.
The aftershock tore up the causeway that linked the observatory to the lake shore. And like the quake that struck Italy in 1997, caused more damage than the original quake. So, what can we do to protect ourselves from earthquakes and the dreadful damage they cause? The obvious answer is for science to find methods of predicting tremors. The problem is that large earthquakes don't happen very often. 10 to 20 minor earthquakes occur in the ground beneath San Francisco every day. But until 1989, there hadn't been a major tremor since the famous earthquake of 1906. So how can science distinguish between the causes of thousands of small tremors and the one big one which can destroy a city?
Earthquakes are probably fundamentally unpredictable. And a key to seeing why that's true is to understand that we don't really want to predict earthquakes. There are 20 or 30 earthquakes every day somewhere in Southern California, just Southern California. What we're trying to do is not to predict earthquakes, but to predict which of the earthquakes we have are going to turn out to be large ones. To be able to do that, there would have to be something different in the way a big earthquake begins than in the way a small earthquake begins. And as far as we can tell, there isn't a difference.
If we're ever going to predict earthquakes, we must be able to measure changes in the earth, which indicate they're about to happen. For scientists, that means collecting and analyzing data before the tremor. And that means getting instruments in advance to a site where one will occur. That's why the tiny community of Parkfield in Central California became the focus of scientific attention in the mid-1980s. Parkfield lies on the San Andreas Fault, and for over a century, a moderate earthquake had occurred there roughly every 22 years. The next one was due before 1993. So the U.S. Geological Survey installed millions of dollars worth of equipment into the Parkfield area. They drilled holes for deep seismographs, installed lasers to measure tiny movements in the land, and video cameras to record the event. Any change in the ground, the tiniest buildup of strain or tilt could be measured. And then they waited and waited. 1993 came and went. Several years later, the earthquake still had not occurred. This is the problem with trying to predict earthquakes. We may, from past evidence, be able to forecast when one should occur, but that doesn't mean that it will. Tokyo has a major quake every 60 to 70 years. The last great earthquake there was in 1923. 143,000 people died. The next big one is now overdue. But there is simply no reliable way of predicting precisely when it will happen. All we can say is that a large quake will almost certainly occur there sometime in the next few years. There are many methods which claim to give warning of an impending earthquake, but for every tremor which does give some advance warning, there are hundreds of others which occur without any early signs at all.
Well, how big an earthquake is depends not on how it starts, but on how it stops. Because the bigger the fault is, the bigger your area is. So if you start here and travel just 10 meters, it's a magnitude 4. Start here and travel 100 kilometers, it's going to be a magnitude 7. And how it stops may have nothing to do with how it starts. And if that's true, we'll never predict them.
We cannot predict earthquakes. All we can do is be prepared for them. Japan has invested heavily in learning centers designed to show what it's like to live through one. Each day, groups of office workers, children, and housewives come here to feel what it's like and to practice the routines they should go through in a real quake. But they're not told that in a large earthquake, their kitchens may just disappear. Some centers even have smoke chambers, where people can experience trying to escape from a smoke-filled house. But this smoke isn't choking and poisonous, and it's not in the middle of a blazing inferno. And there are simulators which mimic actual earthquakes. This one is reproducing the violent shaking of the Kobe earthquake. It's a useful reminder of what to expect, but in a real earthquake, there will be no warning, no time to brace themselves. Once a year, most towns and cities in Japan hold an Earthquake Preparedness Day. Everyone has a role. The Japanese take the annual drill very seriously. But would this ordered exercise be useful in the face of the sudden chaos of a real tremor? If the roads are blocked, water mains shattered, hospitals destroyed, all this preparation might seem futile. The Kobe earthquake caught everyone by surprise. And before the authorities took control, there were several days of complete chaos. These are hard questions for the government to answer, but psychologically, these exercises are important for the people living in the most earthquake-prone country on Earth, to help them feel they are at least preparing themselves. Another challenge is to make buildings and structures safe so they don't collapse. Engineers and architects now use large shaking tables which reproduce precisely the ground movement of powerful earthquakes. Different methods of reinforcing can be tested to see which work best. Some modern buildings now rest on floating bases, which absorb the energy of a tremor. Others, especially very tall buildings, use electrically driven counterweights at the top, which rock in the opposite direction to the shaking. The model building on the left is unprotected, while the one on the right has this system. It works, but it's extremely expensive. Even if the building survives, an earthquake can cause immense destruction to what's inside. In the 1994 Northridge quake, over half the $30 billion repair bill came from damage to the contents. One company in Los Angeles has developed methods for securing the entire contents of any building in the event of an earthquake.
This is a typical angle iron, an L bracket. It's very rigid, and during a severe or moderate earthquake, it can actually pull away from the wall or rip the piece of furniture. The state-of-the-art version is this flex bracket, and it's designed to do just that. That is, flex with the motion of an earthquake.
They have devised a simple but powerful demonstration of the need to secure contents, shaking a room just as it would be in a moderate quake. Then they rebuild the room, securing all the contents.
What you're seeing behind me is a demonstration of a 6.5 magnitude earthquake. The bookcase, the computer table, the table itself, the pictures, the file cabinet, and the cabinet doors have all been secured to mitigate loss or injury. This can apply to homes, hospitals, businesses, anyone who lives in an earthquake zone.
Modern technology has given us a new method of preparing for earthquakes, the early warning system. Shock waves from a tremor travel through rock at about 2 miles a second. Seismic detectors, linked by radio and computer, can register the shock and flash a warning instantly. This could give a city 50 miles away at least 20 seconds warning that an earthquake is about to hit. This may not seem much, but it can be a lifesaver. In the aftermath of an earthquake 100 miles from Mexico City in 1994, rescuers carried pagers linked to the seismographs. When aftershocks occurred, they had almost a minute to get clear of dangerous buildings before the shock actually hit. There were less obvious applications. In the 1989 Loma Prieta quake, some fire engines were unable to get out of their stations because the quake buckled the doors and they couldn't be opened. So now, at the headquarters of the San Francisco Emergency Services, they're using new technology. When an earthquake starts, a special seismograph picks up the first shock wave. It instantly sends out signals, which sound the alarms and automatically open the doors of all the local fire stations before anyone even knows an earthquake is on its way.
Everybody, everybody!
Let's go.
Everybody, everybody!
By the time the quake hits, the doors are already open and the fire crews are moving. This early warning network is growing all the time. The Bay Area Rapid Transit, San Francisco's underground train system, now has seismic alarms to warn the control staff. They can then automatically shut down the system if necessary. Although in the Loma Prieta earthquake, there was no danger at all to the network. Underground in a train was one of the safest places to be. Within the next few years, many other organizations will have these systems: hospitals, offices, schools. All these and many others could benefit from just a few seconds warning that an earthquake is about to strike. Earthquakes have always been with us, and they always will be, as long as we continue to live in parts of the world where they are a threat. Towns and cities will be damaged and destroyed. People will be killed and injured. We can't prevent earthquakes. We know where they are most likely to occur, but we can't predict when they will strike. Living with earthquakes is living with risk. We are truly at the mercy of our raging planet.